Welcome to Newton's law. Gravity has been discussed for many thousands of years. A very early theory comes from Aristotle. And Aristotle proposed that an object, like a rock, falls to the ground because it wants to be near other rocks. This was his theory of the natural place of things. Aristotle lived at approximately the year 350 BCE. And his ideas about physics, called Aristotelian physics, these ideas persisted for almost 2,000 years. It wasn't until Copernicus, Brahe, Galileo, and Kepler, and eventually Newton in 1687, who published his Principia, it wasn't until this date, almost 2,000 years later, that Aristotelian physics was abandoned. Newton recognized that masses attract each other with an equal but opposite force. He recognized that there was an inverse square law surrounding the distance between the two objects. If the distance doubles, then the force reduces by 4 times. If the distance triples, then the force gets weaker by 9 times. There is a square law involved. He also recognized that the larger one of the masses is, the larger the force is going to be. And he was able to combine this in the published law. Whenever we have a proportional relationship, we can turn that into an equation using a constant of proportionality. And the constant of proportionality in this case is known as big G. And this value is on your datasheet. Notice the very small power. This value is tiny. Early estimates were made, and as scientific experimentation got more and more accurate, this value became more and more accurately known. This is the modern value to 3 significant figures. The equation is sometimes written like this. Instead of the upper and lower case version, you need to be familiar with both. In some textbooks, they use specialist subscript symbols to denote particular known objects. Here are a few of them down here. We have the symbol for the sun, so the mass of the sun would be written like this, subscript, and then the symbol for the sun. If we're talking about the mass of the earth, we would be using this symbol, and so on. You may see some of these in textbooks. When doing calculations about large masses such as planets and moons, you want to be very careful with your distances. The distance that appears in Newton's law is the radius. So when we are considering the distance between these bodies, it is the distance between the centers of the objects, and this is known as the radius. If you are considering an object that is on the surface of one of these bodies, then the radius value will not be correct. The distance between that object and the center of this planet would be this distance here, but the distance between the object and this moon would be that distance there. So we would need to use a value for the distance between the two and take away the radius of the planet. in order to get that distance there. Newton's law has also helped us to understand more deeply the structure of the Earth. We know that the Earth is a solid object with a very dense core. But another theory going around a couple of hundred years ago was that the Earth was essentially the crust with nothing in between. It was a hollow shell. And one way to test this hollow shell theory is to measure the density of the Earth, which is mass per unit volume. They knew the volume of the Earth, but they did not know the mass. And they could get the mass by using Newton's law of gravitation. It's known that a pendulum held above a completely flat Earth would be pulled directly downward by the attraction to this mass. If you also have a mountain in close proximity, that also has a centre of mass. So now we have the downward force towards the Earth and a horizontal force toward the mountain, and that would be pulling the pendulum slightly to the side. If we analyse the mountain mathematically and we know the density of the mountain and its mass, we can calculate what this force is. By resolving and using the angle, we can therefore calculate this force and therefore the mass of the Earth. And that's what Neville Maskelyne did in 1774. And they did it with the mountain Schiehallion, which is approximately a conical shape with very flat ground either side and around it. Once the mass of the Earth was known, astronomers could use this value to understand the behaviour of other astronomical bodies, such as the Sun and the Moon. As technology improved, we developed other ways of measuring gravity and therefore the mass of the Earth. Here is an example of a zero-length spring gravimeter. Okay, so we have a spring here, and the force on that spring is the spring constant times by the change in length. The spring is pulling the mass upwards, and the mass is being pulled down by its weight. If you move the equipment above an area of the Earth that has a slightly denser region, then you would expect the mass to be pulled down slightly more than it usually would because of this excess of mass and excess of gravity. Gravity actually changes slightly across the surface of the Earth due to these submerged features like mountains, which would actually reduce the pull of gravity. So here we have a spring system. This is a more detailed diagram of how that works, but this is essentially the basics. More advanced gravimeters use falling masses. So here we have a laser, and that laser is shining a beam that goes to a reflector and then into a photodetector, and that path length is constant. The laser is split at the beam splitter and goes up here, hits the falling mass, comes back down again to the photodetector. And those two rays of light interact and make an interference pattern. As this reflector is falling, this path length changes, and you get a changing interference pattern as time goes by. That can be analysed and used to detect the rate at which it is falling and therefore the value of gravity. Modern gravimeters use superconducting spheres and compare the weight or the force due to gravity with a counteracting force caused by a magnetic field. An analysis of the field needed to keep the object stationary gives you an understanding of how much force is required and therefore what the strength of gravity is. As technology has improved, our understanding of the various properties of our planet and therefore other objects in space has also improved, and we continue to get better and better results, meaning that our observations into deeper and deeper space are also getting more accurate.